Hello. Somebody's watching. Welcome here. I've got the board set up here to do the welcome video, and then we'll just all watch that together really quick, and then we'll get started with our usual Tuesday live concepts on YouTube Live. Hopefully it's totally readable and we have a good connection here. I got my fingers crossed and hoping for the best with all my brand new wires and modems. Okay, so let's do just the intro video part. Hi, welcome to week 8 of Ecological Dynamics. This week we're going to be moving on to two-dimensional systems. Like last week, our interest is going to lie in locating the equilibrium points and defining their stability. So we're going to start this week with a couple videos that teach us how to locate equilibrium points. It's a little more difficult in 2 dimensions because you have 2 differential equations and they have to both be equal to 0 at the same time. So locating equilibrium points in 2 dimensions is going to involve solving 2 simultaneous equations. And typically those equations are going to be nonlinear. And so that's already kind of a difficult topic to start us off for week 8. Your theory of nullclines to analyze the stability of the equilibrium points. We're also going to be able to locate the equilibrium points as we study nullclines by finding them as the intersection of 2 nullclines. And meanwhile, while we're learning all this math theory for 2-dimensional differential equations, we're going to be heavily focused on its applications to ecology. And so the main 2 models that we're going to illustrate the concepts of 2D equilibrium points and nullclines on is we're going to illustrate these on the Lotka-Volterra predator-prey model and also on the Lotka-Volterra competition model. So we're going to get to see these concepts in action right away. So I hope you enjoy all the learning of week 8. How's that? Did I do a good job? Okay, so now we'll go into our usual thing, which is for the live sessions, I've got the live polls up. And we've got a who's here right now. And I see 8 people on the who's here. Welcome to everybody. Thanks for joining us. Oh, great. And somebody's telling me that the picture and board are very clear. And so that is just a wonderful relief to hear that. And I hope that it will always be like that from now on. In a few minutes, once people have had a chance to grab the link and join us, we're going to make our usual word cloud of what we think are key concepts this week. Remember that your concept discussion post, as usual, is due by the end of tonight. And don't worry, don't overthink it. Just take an initial glance at the section and the videos and pick out some key concepts. The word cloud that we'll create next will help you with that. Then we will probably pinpoint one of the concepts that you've named in the word cloud and explain it out. And then we'll have a brainstorm of what you would like to see early in the week and an open-ended chat space so we can chat along while I'm talking about whatever you all want me to talk about. Okay, so let's get started with creating the key concepts word cloud. So I'm going to change the poll now to key concepts this week. And please go ahead and enter up to 3 key concepts for this week. And then we'll start to pick out one of the biggest ones, and we'll explain it in our own words. And while you're doing that, I'll go grab my book and get ready to answer any questions that you have. We are studying section 3.4 this week. Ooh, somebody named the Hartman-Graben theorem. Wow, I didn't see that one coming. That's cool. On page 146, we have the Hartman-Graben theorem guaranteeing that while a nonlinear vector field may have many equilibrium points, each robust equilibrium point is one of the simple types. Remember that last week we learned about the simple types of equilibria, one that's swirling and one that's not swirling. And then there's 2 types of unstable equilibria, one that's swirling and one that's not swirling, again for unstable. And then we have your classic saddle point. So those are the main types of equilibria in 2 dimensions. And yeah, that's nice that we have a guarantee that each robust equilibrium point will be one of those kinds. There's also non-robust, very special equilibrium points. That's not one of the simple types. But maybe those will be, as the author says, mathematically pathological. So maybe we don't have to talk about those too much. Center. I suppose center also is one of the typical types, although I would say that's kind of rare in the real world, but yeah, centers could be one of those types too. Okay, so I've got the section open and ready to go. Just want to remind everyone that when we're working with the word clouds, you do need to connect more than one word with an underscore or a tilde so that it doesn't get broken up. Because I see like a word, like I see the word net floating around, and I wonder if that was supposed to be attached to something else. Mathematically speaking, yes. Okay, so as expected, on the word cloud here, which you can see on our Canvas page, we have nullclines popping out as the big winner. And it's true that those are the big winners. Those are going to give us a bit of global analysis as we look at two-dimensional state spaces. And so I am interested to hear what people would define nullclines as in their own words. Remember, that's part of your concept post assignment, is to try to explain some of these concepts in your own words. Multiple equilibria or stability changes and competition models. Those are all great concepts too to choose for your concept post. But I'm going to choose for our next question for us to share out nullclines. Explain nullclines in your own words, because that is kind of the most popular concept for this week. Looks like we've stabilized in our word cloud entries here. Last chance. I'm not sure if anybody out there is still entering something into this word cloud, but I'm going to switch it over to, and let's switch it over to the next one. Okay, so now I've replaced the concept. This chosen concept for this week is going to be explaining nullclines in your own words. And not only will that give you some practice and comfort with one of this week's top concepts, but it'll also give me some information about how you're absorbing it and what you understand it to mean so that I can help teach you as well. So go ahead and participate in that one and try to talk a little bit about nullclines in your own words. Just what they mean, especially if you're in the ecology part too. You were actually introduced, if you're an ecology student, to the concept of nullclines last week in your ecology book. They're known as isoclines in the ecology book. And somebody mentioned that those were probably going to line up, and you're right. Those originally Carrie and I had planned to teach synchronously, but as I started to feel out how it was going in the class and I kind of slowed down my curriculum, that's why my treatment of nullclines is 1 week behind the introduction in the ecology curriculum. Yeah, but it's still nice to kind of see them both mesh. And so if anybody wants to add in a perspective from what they read in the ecology textbook, that will be great too. And I'm just going to kind of read off some of the responses so far so you can get a feeling for how people see and understand nullclines. So one person says a nullcline is a line in a two-dimensional vector field, the length of which represents zero rate of change for one of the state variables. A perfect explanation. Excellent. Then we also have where a variable on a state space is equal to 0, such as x prime is equal to 0. Right, and so remember that the thing that's equal to 0 on a nullcline is not necessarily the variable itself, but it's the rate equation for the variable. And so where it says x prime is equal to 0, that's going to be the nullcline for x. But it doesn't necessarily mean that x has to be 0 at that time. It just means that the rate equation x prime or dx dt is equal to 0. Someone has said points where the vectors are either straight up or straight down. And that's a good explanation for one of the nullclines. And I'm thinking through that statement. If I have a point in the vector field where the vectors are always straight up or straight down, whose nullcline am I on? Am I on the x nullcline or the y? I'll leave it open for now for people to think about. Someone else has said modeling multiple equations in 2 dimensions in order to identify equilibrium points and determine their stability. And that's a great discussion of what nullclines are used for. But in case you're worried that you would need the nullclines every time you want to know the stability of an equilibrium point in higher order dimensions, that's not necessarily true. I know that we're going to go through a lot of hand crunching of drawing vector fields and figuring out the arrows on the nullclines this week. But as I provide you with some optional learning in the coming weeks ahead, if anybody is curious and wants to look in chapter 6, where we talk about linear algebra, there's actually a linear algebra way to analyze stability of equilibria in higher order dimensions. It's the same thing that we learned last week when we learned linear stability analysis. That same concept in 1 dimension scales up rather nicely in n dimensions, but it requires the use of what's called linear algebra, which is kind of an extension of the algebra that you're used to, but it allows us to analyze multiple dimensions. So there's more than one way to figure out the stability of equilibrium points, but in 2 dimensions, this is a really nice way that not only gives you that stability, but also gives you a bit of a global picture of what's going on as well. Another person said a place where one of the variables in the state space has a derivative of 0 to see how the trajectory of the other variables is changing on those lines. Excellent. I love the explanations you're providing in your own words. And someone else has said nullclines are the lines in a vector field for a function when change is only occurring in one variable. For a 2-dimensional system, it's lines along which either x prime is equal to 0 or y prime is equal to 0. Awesome job, everybody. Thank you for submitting those explanations. And for those out there who are concerned about their concept discussion posts that's due tonight, this is a resource for you. So don't forget to check back to the YouTube Live 519 page on the Canvas module for this week. And this should be a great starting point to help you get some ideas of what to post by the end of the night. So I'm going to move on to the next question right now, which is the classic brainstorm of what you'd like to see. And really, you can either enter a suggestion of something for me to do. It could be a problem set. It could be explaining a certain box or page on the in the section that you're supposed to read. It could be going into more detail on something you saw in a video. Really, any suggestion is up for grabs here. And as the suggestions start to roll in, you can vote up or down on any of the suggestions. So far, I see some requests for some of the problems for this week, which is awesome because it tells me that you are starting your problem set on a Tuesday. And it's not due till the weekend. Yeah, you're going to have a great weekend. Let's get this math out of the way during the week. And that way we can save the weekend for reading extra math or maybe other math books. Who knows? Or maybe we'll just read about math pages on Wikipedia. Yeah, so we'll free up our time by getting these questions answered at the start of the week. And I'm just going to take a look at questions 3.45 and 3.46 so that we can go over those. Right. Oh, okay. Examples here. Okay, so I will definitely touch upon these questions, but I'd also like to mention that the procedure that I'm going to go over right now live for you is also the procedure that I have previously made a video on for our Week 8 playlist. And so don't forget to use the videos in my Week 8 playlist as one of your main resources for figuring out how to find 2-dimensional equilibrium points, and that's question 3.4.5, and for sketching change vectors on nullclines in 3.4.6. That's exactly what I do in the video, but I think it would actually be a good exercise to kind of go through that again with you all while you're watching live, but have you play along. I think what's going to make the difference here and make this a really constructive session is that we're going to write down the model that's named on page 142. That's the request coming in from the polls. And we're going to play along together. So I don't want to just record myself doing it like I did last time, but I'll be trying to ask you leading questions. And I see 12 people watching right now. So everyone who's watching, get out your paper and pencil, get out your math book. We're going to do your homework live on a Tuesday, and we're going to get some of this stuff done. It's going to feel really good to get some of this earlier questions out of the way really early in the week. So those are pretty much the only requests I see coming in. So I'm going to switch it over to the open-ended chat space now so that we can have a conversation while we go through these questions. If at any time somebody wants to enter another request for an additional thing for me to do, you can go ahead and use the open-ended chat space at this point to contribute that. But I'm going to start us off by going to page 140 recording of the video. When you look on the playlist for week 8, I have already thoroughly gone through the example that's on page 140 and 141. And so if you are trying to do the exercises 3.4.2 or 3.4.3, those will be in the video playlist. And also in the playlist, I made a final video that kind of compares the two deer moose models. But now we're going to go into detail on the second deer moose model, which is actually the one thing I left out of the videos. So great job naming that request. And let's all work through this one together. Okay. All right, we're going to start by just copying down this equation. Now let's consider a new version of the deer moose competition model with different parameters. So here's the new version right here. Okay, for ecology students, it might be fun for you to recall what the parameters of this equation where I start out with the first version of this model, and I kind of reorganize the terms so that you can see the fact that this is a logistic model combined with an interactive term that is detrimental to both species. So in both cases, we have deer and moose growing logistically on their own, and then because it's a competition model, every time they interact, they both kind of lose out because they're meeting in the same grass field and fighting over the grass or something like that. So I'll leave that part out, and I will just go straight for the questions. 3.4.5 says to find the model's equilibria, and 3.4.6 says to sketch the vectors on the M nullcline. Okay, so let's start at the beginning where we're going to find the equilibria. Find all the equilibrium points. And like I was saying, I really want this to be more of an interactive mode than just watching me do it up here. So I've got the open-ended chat space up here live, and I'm watching it. I don't see anybody typing anything in yet. But what I want to ask you right now is, how am I supposed to do this? I want to see what kind of suggestions people want to provide for find the equilibrium points. There's multiple different approaches that we could take to find the equilibrium points, and I want to know which direction you'd like to see us go. The main two directions would be algebraically or geometrically. And I've kind of made videos about both, but I want to see which way you want to play it. Oh, nice. You're fast. The first comment I have here on the open-ended chat space is factor it out. That's an excellent suggestion because when we're working with nonlinear equations, keep in mind this is nonlinear because it has terms besides linear terms. And when we do have nonlinear equations, it'll be easier to set those equal to 0 if they're in factored form, because that way we can just set the factors individually equal to 0 as opposed to, you know, maybe you think you should try the quadratic formula because you see quadratic terms here. That's not what you want to do. You want to try to factor it out. Great suggestion. So I want to work with that suggestion and encourage everyone to factor it out. Okay, and before I do that, I'd like to see you try to do that. So what is the common term for the d prime equation that you would factor out here? Likewise, what is the common term for the m prime equation that you would factor out there? So go ahead and start working with those on your own page because you're basically doing your homework right now. Way to go, getting a head start. And then in a second, I will start to factor it out. If anybody wants to add a hint into the chat box for the d prime equation, I'm going to pull out the or something like that. Excellent job. Excellent. So I hope that everybody is also watching our YouTube live results page on our Canvas site because you're going to see some great hints here. And someone is saying for the d prime equation, we're going to factor out d. For the m prime equation, we're going to factor out m. And they already did the d prime equation for us, factoring out the d. Awesome job. That's exactly what you're going to want to do. So we're going to factor out the d here. And we're going to go 3 minus 2m minus d on the inside there. And then on the m prime one, you're going to factor out the m. And people are entering that right into the comment box, playing along. That's wonderful. So we have the m there. And then we're going to do 2 minus d minus m. Okay, after you've factored it out, it's always nice to do a quick double check. So I kind of just like look at it and make sure that if I refactored it in, I would get the same exact thing that I started with. So I'm just kind of double checking in my head. See my fingers illustrating that I'm refactoring it, making sure I'm good to go. And that's perfect, right? Okay, so I remember last week we had some good conversations about pretending we were at a fancy restaurant. Maybe someday we might get back to one someday. Or we could make a pretend one at home, which is what I'm doing with my kids. And we have to make choices, right? Because there's two factors here. So we're going to make a choice. Either I'm going to set this factor or this factor equal to 0 for my first choice. And then for my second choice, I'm going to pick either this factor or that factor is equal to 0 for my second choice. Because this is going to get so complicated, I really want to start using multiple colors. Okay, so I've typically been using blue for the first variable's nullclines and then red for the second variable's nullclines. So I'm going to stick with that and I'm going to start using colors, even though I'm just doing the algebra right now. So I'm going to set that one equal to 0 in blue, and I'm going to set this one equal to 0 in red. And I'm going to write out the two choices for each. And as I write out the two choices for each, then we're going to pick and choose, see how many equilibrium. One of the blue choices and one of the red choices. Okay. Once again, I highly encourage you to play along. And so I wonder, does anyone remember me doing this from last week? Remember, and I was like, the blue one is like the appetizer, and then the red one's like the main dish, and you have to pick one of each. And then we got a little confused, but I think it was a healthy confusion for everyone because it had a good lesson behind it, which was that when we were doing this last week for the predator-prey model, I think it was actually 1 week ago, and we got cut out shortly after that, is I was trying to make the choices, and at first I thought there was going to be 4 choices, and then I realized that there was only possible to be 2 choices for the predator-prey model. This is a competition model, though, and if you've been doing the reading in the book, especially if you're looking at figure 3.24, you can see that this is going to result in 4 different equilibria. Okay, so if you're playing along, make sure that you have page 142 open, and you're looking at figure 3.24, in which we will visualize the nullclines after we go through the algebra of deriving the equilibrium points. Okay, so for the blue track, we're going to have 2 choices. And I wonder if anybody wants to enter those choices into the chat box to make sure that you know what I'm doing. and I know what you're doing, just like in a real classroom. What are my two choices for the blue lines that are going to be the D nullclines? I'm going to have to set the factors of the D prime equation equal to 0. Then you see there's one factor right here, and there's another factor right there. Okay, so if I set that one equal to 0, D equals 0 is my first choice. Because I set this factor right here equal to 0. That's what I got my first choice. Right, and then the other one is you set the other stuff inside the parentheses equal to 0. Excellent. So then the other choice is 3 minus 2m minus d is equal to 0. Perfect. Yeah, that's exactly the two choices we have for our blue. And then for red, we're going to do the same exact thing. And it's lucky that we have it in factored form, because that's what allows us to be able to do this, is the fact that the product of two things equaling 0 is just either one of the things equals 0 or the other thing equals 0. So for this red one, we have the two lines that either m is equal to 0 or 2 minus d minus m is equal to 0. Okay, great. And so now we're going to try to pick and choose from that. And I would invite you, as you're playing along, to enter any points that we find algebraically into the chat box. One of those fixed points is going to be the real easiest one to pick. That's going to be to pick choice number 1 for the blue and choice number 1 for the red. That's going to give us our easiest fixed point. And so what are the equilibrium points? I'll start making a list of the equilibrium points down here at the bottom, and we're just going to go through these one at a time. So choice number 1 here and choice number 2 there gives me 0, 0. And if you're playing along with the figure in the book, you're going to see that one. Just in case anyone happens to be watching this video and they don't have the book, I'm going to give you a nice shot of the corresponding nullclines graphed in the state space right there. And you can see that choice number 1 of blue and choice number 1 of red leads us right to the origin spot right there. Right, 0, 0. Okay, so now let's see what other kinds of things we could choose. Like instead of choosing number 1 for the blue, maybe I'll choose number 2 for the blue. Okay, so for my second equilibrium point, I will choose this one, but then I will still choose choice number 1 for the red. You see, I'm trying to do this systematically. And so taking this one right here, looks like I would need to solve this simultaneously with this one over here. For each of the remaining 3 fixed points, there's going to be a little bit of simultaneous linear equation solving, a little bit of chicken scratch going on. So I'm going to use this board over here as my sideboard. Okay, so I'm just going to keep track of the choices that I'm making and the resulting equilibrium point that comes out of that using this board for the side work. So for my second one, I'm going to pick D is equal to 3 minus 2m. Okay, actually, that's not, usually we write it the other way. So actually, before I begin here, because I know that the next thing that's coming is drawing the nullclines, I'm actually going to take these 2 more complicated forms, and I'm going to try to write them in the same way that I would graph a line, because I know that eventually in the state space, I'm going to have m on the vertical axis, and I'm going to have d on the horizontal axis. So m is kind of like the y variable, and d is kind of like the x variable. So if I want to write this in a format that matches y is equal to mx plus b, I'm going to solve it for m. That way it'll make me think about a line. Okay, so I'm just going to solve this for m by moving m to the other side and then dividing the whole thing by 2, like that. And then this one over here, again, I'm going to solve for m because that's the y-type variable, and I'm going to get that kind of form. Yeah, that's just going to make it a little bit easier to think about graphically later. And for now, I'll show you which 2 choices I'm picking. I'm picking the second choice for the blue, and I'm going to stick with my first choice for the red. Okay? M is equal to 0. Oh, okay. So it tells me right off the bat that m is equal to 0 for my second equilibrium point. M, that's the second variable, right? So if this red one tells me m is equal to 0, I'm just going to throw the 0 right into the m position there. And now I can see that the value for the y-type variable m is going to be 0. And then I need to know the value for the x-type variable there. And so I'm going to go over here. And I'm going to plug in at the assumption that m is equal to 0 into the blue nullcline. You see, since m is equal to 0, I'm going to do that. I'm going to set 0 equal to 3 minus d over 2. Okay? Now, I want to make sure that everybody understands what I did. And usually this is kind of the first place people get copied, that m is equal to 0. And that's where the m appears in the blue line. So I'm basically solving these two equations simultaneously. And by multiplying that by 2, I get the conclusion that d has to be 3. And so that's going to be my second point right there, is 3, 0. Okay? And so we're setting d is equal to m. Good question. Thanks for sending your question in through the chats. What we're doing when we're trying to find the equilibrium points is we're trying to set them not necessarily equal to each other, but we're setting the equations equal to 0. Once we set both of the state equations equal to 0 separately, then we start to get these different directions that we could go. And we have to pick one direction to go for the blue. In this case, I chose the downward version of blue. And then we need to pick a direction for the m, in which case I chose the upward direction. Okay? And then what we're doing there is we are solving these two things simultaneously. Okay, so we're not necessarily setting d equal to m. In fact, if I did set d equal to m, because I chose the red nullcline where m is equal to 0, if I set d equal to m, then d would also be 0. And that would just get me back to the 0, 0 point that was my choice when I picked the upward route for both the red and the blue. But this is the case where I picked the downward route for the blue and stayed with the upward route for the red. And so I have to just solve these two things simultaneously. So let me just write that on the board to clarify it. I appreciate the question. So make sure we really stay on track here. We need to solve these two equations simultaneously. Okay, so these two equations have to be true at the same time. One of the statements is really easy, m is equal to 0. That's pretty straightforward, so that one's basically already solved out. But in order to solve this one at the same time, I have to replace the letter m in this equation with the assumption that m is 0 that comes from the second equation. So that's what we're doing, and it's not true that we're setting d equal to m, because like I was saying, if I did implement d is equal to m here, the fact that m is equal to 0 would lead me back to 0, 0, because then d would also be 0, okay? But the work that you see me doing on the board right here corresponds to this fixed point, the second equilibrium point that's located at 3, 0. Just checking back in with the picture so you see where we are. If you're following along with figure 3.24. Great. I hope that cleared up the confusion. Keep using that chat box anytime you have a question. Keeping my eye on that for sure. And I hope everybody's okay with how I got the 3, 0 point. And I'm going to move on to the next point now by trying to choose a different direction. Right? So I already chose up and up. And the next thing I did was I chose down and up. And so now the other thing I could do is I could choose down and down like that. Or I could choose down for the red and up for the blue. You see, there's 4 different ways that I could play this. When you choose down and down, that's the hardest way. So I'm going to save that one for the end. Okay, so the next thing that I'm going to do that I haven't done yet is I haven't chosen to go up for the blue, but down for the red. Okay, so that's the next combo I'm going to do, is choose up for the blue and down for the red, just because it's a little bit simpler. Okay, and again, I'm going to be doing my side work on this board over here. It's great to have good internet so that I can make use of both of the boards at once here. So like I was saying, I'm going to choose to go up for the blue and down for the red. I haven't chosen that one yet. If I go up for the blue, I'm going to get D is equal to 0. And if I go down for the red, I'm going to get M is equal to 2 minus D. Okay. Now, can anybody tell me the equilibrium point that results from solving these two things simultaneously? This is a little bit simpler than the last one because the non-zero nullcline has a simpler form. And once again, in order to solve these two things simultaneously, one way to do that is to take the assumption from one equation and plug it directly into the second equation. Assumption that D is equal to 0 right into that equation there. And so I'll just write that on the board. Plug D equals 0 in here to this equation. And so I get M is equal to 2 minus 0, which means that M is equal to 2. Right? I plugged in D is equal to 0 because that was one of the equations. So I took one equation, plugged it into the other equation, and then I get M is equal to 2. It's really important that I don't mix up D and M. Then again, everybody makes mistakes, right? And so I've done this a lot of times where I'm solving for nullclines, and I'll kind of get it flip-flopped, like what is equal to 2? And I see someone has typed into the chat box, D is equal to 2. It's really important for us to mention that because it's a very common mistake that gets made in nullclines. Don't feel too bad about it. Just know that you're helping everyone by giving us some examples of common pitfalls, okay? And so keep in mind that when we're doing this, we have to remember which variable is which. That's why I try to use two different colors. So D is the blue one, right? And D is already equal to 0. When I plug that assumption into this nullcline, then I get the statement that M is equal to 2. And finally, when I write that all down here, because I'm trying to make a list of the equilibrium points, I better not mix up which one is 0 and which one is 2. Found it helpful. Ah, thank you. So someone's given a really good hint to help us as we try to work through this and not get confused about which is which. The hint says, I found it helpful to write D comma M off to the side to remember which axis they're on. Extremely helpful tip. Thank you. So I'm going to do that right now so that we can keep that in mind. So all of these points are in D comma M format. And I'm just going to write that underneath every single one because I know that that will help me match them up. There's going to be 4 of these all together. So here's space for the third and fourth one. And I'm going to just, right underneath it, I'm just going to remind myself that these are all in D comma M format. And let's see where I can fit a little reminder on the board here is that if I was going to be graphing the state space, I would be doing D on the x-axis and M on the y-axis. And so all points are going to be in D comma M form. That's super helpful. Thanks for reminding us there. So going back to our work over here, where it says D is equal to 0, if I actually wrote the form, the XY form right underneath it, I'm less inclined to make a mistake. See, D is 0. And then here I concluded that M was 2. And so I'll just put that right on top of the M. So 0 comma 2. Again, it's really common to make a mistake where you might mistakenly think 2 comma 0. Or you may have mistakenly thinking 0 comma 3 here. So we just have to use any tips we can to make sure we keep it straight. And that's really helpful. The other thing that I find extremely useful is that I'm always trying to do algebra because you see a lot of letters and numbers, mumbo jumbo on the board there, but I feel like happens visually. I really like to think in pictures. And so you always want to keep this figure in mind. If you're doing this problem yourself, I would highly recommend that you're drawing out the nullclines that are represented algebraically on the board over there. you're drawing them out in the plane, because then you can see the things that we've been locating. See, once again, we have 0, 0 right here. And then we have 3, 0 here. And then we have 2, sorry, see, I just mixed it up. 0, 2 right up there. And you'll see those on the picture, which will help you match your algebra to make sure that you're expressing it right. Great. I'm really glad to have you all here and to give your tips in as well as what I've known to be helpful. Now we just have to locate this final one right here. Okay. Now, if you're looking at the figure, I know you can see it, but let's practice the algebra of it, because honestly, the parameters that were chosen for this problem are not probably ecologically realistic. If I found this problem in an ecology book, we've already seen that competition models in ecology books have a lot of different parameters. I think there's 6 parameters in total, right? And usually those parameters are matched to field data by using statistics. That's a whole nother part of this course here. So it's really nice to see the holisticness of putting it all together. And the parameter values are usually not going to be whole numbers like 3, -2, -1. Oh, that's so convenient. But that's probably not how real deer and moose work. They're going to be really nasty numbers that are going to be hard to do. And so, you know, the number's not going to pop out like 1, 1 that you see here. So it's always good to practice the algebra too, so that you can derive the exact form of the fixed points. In fact, I think that I did that. And if you look at my week 8 playlist, I did provide an optional video in which I algebraically solved for this fixed point here where both of the species are non-zero. So this is the fixed point of coexistence. And if you see my optional video in the week 8 playlist, you'll see that I solved that out in full generality using the format that ecologists use that I got from the ecology textbook. And it's messy. So let's just practice it with a couple numbers in play right now. Okay, so for my final one, I'm going to choose the down root for both of my choices. So I'm going to choose to go down for the blue, and I'm going to choose to go down for the red. So that's going to be the most complicated one, because for both of those, it doesn't really say anything. Like, it doesn't say like one of the things is actually a number or anything. It just says equation for the blue, and then it says equation for the red. Okay. Now, hopefully you've seen the topic called solving simultaneous linear equations from pre-calculus learning at some point. And there's a number of different techniques to do that, but I'll just choose one way to go. I'm trying to solve both of these at the same time. What's convenient about this for me is that I've already put them in the y = mx + b format. So for both of these equations, I have a statement m equals a function of d. M equals a function of d. And if I want these to be equal at the same time, because it says m equals on both sides, I can just set the two right-hand sides equal to each other. Okay, that's one of many ways to solve simultaneous linear equations. Hopefully you understood what I just said. Please let me know if you didn't, or if you have a question about, or maybe an alternative suggestion about to connect with me. Let me know if you want to see it a different way, or if you just have a question about what I'm doing. Okay, so I'm going to set them equal to each other because they're true simultaneously. So 3 minus d over 2, that's the m on the blue, and 2 minus d right there, that's the m on the red. See, so I just set both their right-hand sides equal to each other. Again, the reason that I can do that is because I put them both in the form where m is equal to them, right? So I'm saying m equal to m. Okay, so I'm just going to multiply both sides of this equation by 2. So I get 4 minus 2d here. Okay, and then I'm going to bring all the d's to this side and bring that to that side. And it's going to give me the fact that d is equal to 1. Right? If I add 2d to both sides, I get just 1d on that side. And if I subtract 3 from both sides, then I get 4 minus 3. So I'll just show that out. So I'm subtracting 3 from both sides, and I'm adding 2d to both sides. So these are the two operations that I'm doing to both sides of the equations. And that leads me to the combination of like terms here being 1d, and the combination of like terms here being the number 1. Okay, so I got d equals 1. And luckily, I'm implementing this very helpful suggestion from a student that says I should write d comma m underneath, so I don't mismatch the values. D is equal to 1, and the d is the first component of this two-dimensional vector, and so that's just a 1 right there. And now I'll solve it out for the m. In that case, once you've found the value for one variable, you can plug in this value either into this one or into that one, and you'll get the same answer either way. So you see, if I plug in d is equal to 1 here, I get m is equal to 2 minus 1, which is equal to 1. So here's where I got the conclusion that m is equal to 1. But if I plugged in d is equal to 1 right here, I would have gotten 3 minus 1, which is 2, over 2. So I still would have gotten m is equal to 1 either way you slice it. And so that finishes off the problem with the final fixed point, the only fixed point that represents coexistence. And again, matching it to the table. Okay, cool. So I see some people are still watching, which is great. And now I'm going to go into 3.4.6. And after that, if that's all the help you would like for today, then we'll just take a break and make sure that you submit your concept discussion post by the end of the night. If you have any other things that you would like explained or talked out besides 3.4.6, now's a good time to put them in the open-ended chat space, because that way I'll know that there's more things being requested, and I can prepare for them, okay? So please put in any other requests that you want in there. And besides that, we'll just use this procedure, this test point procedure that they do to sketch the change vectors on the M nullclines. Okay, if you look at my videos, you'll see that I have a suggested alternative. Instead of using the test points, I make this little graph that kind of helps me figure out what the change vectors are. I wonder if there's a method that you prefer, or if there's one or the other way that you'd like to see it done. I'm going to set up the problem right now, and if anybody has a preference, like if you want to see me use the method in the book, you can let me know that, or if you like that visual method that I derived, that I made use of, I can talk that out some more too, see if there's any questions to that. Okay, so just let me know if you have any preferences there. And I'm going to erase most of the board except for the M nullclines, and then we're going to sketch the M nullclines and overlay the change vectors on top of them. And you can see kind of the answer to it is right there in figure 3.7, but we're going to explain it out right now. Okay. All right, let's copy down the M nullclines here. And now we're changing the problem to be 3.4.6, which is sketch the M nullclines. And put the arrows on them, with the arrows. Okay, so the M nullclines were the nullclines for the second set of variables. I'm confused by how the numbers were found. Thank you. That is very helpful for me to know. Okay, so you know what? Let's talk, as I go through this, I'm going to talk out the method of test points that's laid out in page 144, and I'm going to discuss how they got the change vector points and also why they chose the particular test points that they did. I'll try to explain that out, and that is based on the comment that I had in the chat space. Thanks a lot. Those are so helpful for us to engage together and for me to know where your sticking points are. So keep entering your comments into that chat box as I set it up, and I will explain what Alan's talking about here when he says he's picking some seemingly random points on which to evaluate the vector fields. Okay, so we're talking about the M nullclines here, M nullclines, and there's two of those. There's M is equal to 0, and the second one is M is equal to 2 minus D. We're going to draw those in our state space where our horizontal axis is D and our vertical axis is M. So the first thing I need to do is just draw these suckers on the board. And okay, it's true. Sometimes I get confused when it says M is equal to 0. Is that a vertical line or is it a horizontal line? So let's just double check and make sure that we get that part right. M is the vertical axis here, right? And so when M is equal to 0, that results in a horizontal line, right? Because like this is M is equal to 1, M is equal to 2, M is equal to 3. And so those are all horizontal lines. So M is equal to 0 is this horizontal line. Just like if it was an XY problem and I asked you to graph Y is equal to 0, that would be a horizontal line. D is equal to 0 would be a vertical line. I agree. I'd also like to hear how to select test points and review the other method too. Great. Yeah, so we'll definitely go over both ways. I'm so glad to see that you're still engaged and you're still playing along with me. Okay. So this line here is technically supposed to be right on top of the D axis. I just drew it hovering above so that you can see it, okay? But just make sure that you know that that is literally on the axis. Okay, and then the other one right here, 2 minus D, it has a y-intercept of 2, and it has a slope of -1, which leads you to a d-intercept or an x-intercept also of 2. And so this other one that I'm going to draw is going to look like this, where it hits 2 right here. So it has an x-intercept of 2, and it also has a y-intercept of 2. This is the line M is equal to 2 minus D. Okay, so when it says to just sketch the nullclines, there you go, you sketch the nullclines. But when it says to sketch the change vectors on the nullclines, that's when it starts to get tricky, okay? So we got to sketch the change vectors on the nullclines. When we're doing this, it's really, where I like to start is to think about which way are these change vectors going to be pointing. So before I even begin with the work of the problem, I want to ask those of you who are listening, are the vectors that I sketch on, because it has to, either they're just always going to be left or right, or they're just going to be up or down. Because remember that nullclines are the places where one of the components for the change equations is 0, and the other one is non-zero. So left and right behavior, the left and right components of the vector field are dictated by the equation for d prime. And the up and down behavior, or the second component of the change vectors, is predicted by m prime, and we're working on the m nullclines. So I just want to pose this question to you all right now. Are these going to be on the m nullclines? Is the vector field up and down, or is it left or right? Is it up or down, or is it left or right? Because if I don't know that, then I don't want to move any further because I'm not going to know what to draw. Okay, so you got to think about how am I going to answer this question? Let's see. One of the vector field components is 0. So think about which vector field component is 0. And then the other one, what does it represent? Left or right or up or down behavior? Left or right? Yeah, excellent. Yeah, it's going to be always left or right because the D prime is not 0 on the M nullcline, right? And the D prime, because D is on this axis, represents left and right behavior, right? The up and down part is represented by the M prime, but the M prime is 0, so there's no up or down. Exactly right. Great. So we have 3 people responding that it's left or right. Really good. I'm glad that you're right on track there. So the vector field is just going to be left or right, okay? Now that we know that, it helps us figure out how to proceed, and it also confirms our understanding that what we are supposed to be doing next is we're supposed to be picking points that lie on the nullcline itself, and we're supposed to be plugging in one of those points into the D prime equation. If you accidentally plug it into the wrong equation, you will get 0. And if you get 0, you won't know what to draw because it's neither negative nor is it positive. So that's another way to check and know that you're on the wrong route, is if you do what I'm about to do here and you get 0, then you picked the wrong way to go. But it's good to just know that, as my goal is here is that's left or right behavior. And so what I'm going to be doing is I'm going to plug in test points on the M nullcline into the D prime equation. Okay? So I'm going to be plugging in test points that lie on the M nullcline, and I'm going to plug them into the D prime equation. And that's going to tell me whether it's going left or right. There is no up or down component on the M nullcline. That is indeed what defines it as an M nullcline, is that there is 0 behavior in the up or down direction. Okay, cool. So let's start with the easier ones, and then we'll go to the harder ones. So I'm going to start by explaining the procedure on page 144 that involves... Hold on a second. Sorry, my bad. I misspoke. These 2 test points here are actually evaluating the D nullcline. I'm sorry. So I just made a mistake there. Actually, as I read through the page here, everything that they do for the test points on the top of page 144, this is all for the D nullcline. Well, that makes sense because then they give you an exercise that asks you to do the same thing that they just did here, but they ask you to do it on the M nullcline. Okay, so what you see me do is I'm going to pick different test points than they had up here because they're doing this work for the D nullcline, and I'm going to repeat their work, but on the M nullcline instead. So we should not try to pick the same test points that they used because they use points on the D nullcline. Okay, so we're going to pick our own points for the M nullcline. That's what we're going to do. Okay, let's do our extra work over here. So we're going to start with just the M is equal to 0 nullcline. Okay, and we're going to pick some test points. Oh, geez. You know what else we should know? Here's something that's really important for us to know, is that as we do this procedure, you'll see this in my other videos too, the nullcline, the arrows on the nullclines change direction after we've gone through an equilibrium point. So one more piece of information that I want to put on the board before I start to choose test points is I want to know where the equilibrium points are, because then I'll know to choose different test points for each side of the equilibrium point. Okay, that's a really important thing to know. So I'm going to draw, luckily we just did that in the previous question. We just did that in 3.4.5. So I'm going to lay the equilibrium points on top of the nullclines, keeping in mind that the arrows will change direction every time you go past one of those equilibrium points. Okay, so some of the work that we did, oh geez, I'm not going to have enough room. I'm going to move this over a little bit more to make sure that we have enough room here. that we need to go all the way over to 3 in the D, because here's the number 3 in the D. Okay. There's one equilibrium point right here. There's an equilibrium point at 3, 0, right? There's another equilibrium point at 0, 0. There's another one at 0, 2, and then there's another one right here at 1, 1. Now I'm going to write what I just said on the board to make sure that you know why I chose to pause what I was doing to draw the equilibrium points. And what I was trying to say is that arrows on the nullclines change direction when passing through equilibrium points. That's a really important thing to know, because like we were just saying, there's going to be left or right behavior on these things, right? But let's say that I use the method of test points and I find that it's pointing to the right along here, and it's still pointing to the right. Once I hit this equilibrium point, on the other side of it, it's going to flip, and then it's going to point to the left. That's typical behavior on equilibrium on nullclines. Again, let's say that the vector field would happen to be pointing to the right here as I'm on the M nullcline. Once I go to the other side of this line, it's going to flip its direction, and then it's going to point to the left. Or vice versa. Sorry, it's vice versa for that. First it's pointing to the left, then it's pointing to the right. Either way you slice it, the important thing to know is that the arrows in the nullclines are going to change directions when the nullcline passes through an equilibrium point. Okay? So that way we know how many different regions we need to test. Okay? We'll see that as we go through the analysis too. We'll see that statement kind of emerge from the analysis. Okay. So again, I'm working on the M is equal to 0 nullcline, and I'm going to plug M is equal to 0, which is the nullcline that I'm working on. I'm going to plug that into the equation for D prime, because that's going to tell me whether it's left or right behavior. Okay, so here's the D prime equation right here. D prime is equal to D times 3 minus 2M minus D. Now I'm going to plug in the fact that M is equal to 0 here, because I'm working just on the M equals 0 nullcline. So that tells me that, here's the M is equal to 0 nullcline. The conclusions that I'm about to draw from the algebra that I do on this board, they apply to the vector field only along the line M is equal to 0. That's because I'm plugging in the assumption that M is equal to 0 directly into the rate equation for the other variable. Okay, so this is not going to be a global statement about the vector field. It's only going to be true about the vector fields on the line that I plugged in the assumption for. Hopefully that makes a lot of sense. As usual, questions are always welcome in the chat box. So if anything I say is confusing, definitely don't hesitate. Just throw it right in there, because I'll see it right away, and then I'll know to respond to it, okay? So I'm going to plug in M equals 0 here, and I'm going to get D, and then 3 minus 2 times 0. That's where I plugged in the assumption that M is equal to 0, minus D. And so that tells me that D prime is equal to D times 3 minus D. Okay? I'm going to try to analyze this by displaying it graphically on this picture right here. Okay? So remember that I'm just working on M is equal to 0. So on M is equal to 0, nullcline, I have the statement that D prime is equal to D times 3 minus D. Right here. Now I'm going to explain the method of test points, and then I'll explain the graphical method that I introduce in my videos. And thank you for the comment. That's just a nice comment that says walking through it step by step is really helpful. You're welcome. I'm glad to be being here right now, or watching it as soon as you can afterwards. If you're watching this afterwards too, that's great. But working on this early and often is so pivotal to your success. So great job. Thanks for the comment. So let's go to the method of test points first, okay? And so we're going to use test points to determine whether it's right or whether it's left. Remember, it's either going to be right or left behavior. Strictly right or left behavior, because that's what the D prime equation dictates. It talks about the horizontal behavior of the vector fields. Yeah, no problem. Glad to be here. Okay, remember, we're on this line. And so, like, from what I was saying before, we know that at this point, this equilibrium point, whatever was happening over here is going to switch, and it's going to do the opposite thing on the other side. So when you use the method of test points, you need to locate a test point in this region, in between these two equilibria, and then you have to pick another test point that's in that region. The equilibrium points are breaking up the nullcline into regions of different behavior for the D prime equation. Okay, so let me write that on the board what I was saying. So between here and here, I need to choose a test point. Choose a test point here and here, okay? And then between here and here, I need to pick a different test point. Test point for here. Okay, now that part is really important for you to understand. So do you see what I'm trying to say? The equilibrium points that are located here and here are breaking up the behavior of the vector field into two qualitatively different regions. There's going to be one region here between 0 and 3. And if I choose any test point, whether I choose this point or that point or that point, it doesn't matter. I could pick any one of these test points. And they're all going to share the same sign for D prime. Either I will conclude that D prime is positive, or I will conclude that it's negative. And then once I leave this region and I go to the other side of this fixed point, the behavior will be different over here. So that's why I have to pick a different test point for that region. Okay, so we'll start with region number 1, and then we'll go on to region number 2 over here. Okay. So we're still working on the m is equal to 0 board, and we're just testing the sign. Okay, so we're going to do a test region number 1, in which case D is between 0 and 3. And then we're going to go on to test region number 2. Okay, I really want to interact with you as much as possible. So now, just to make sure that we're all on the same page, can anyone volunteer a suggestion for a test point that's going to work? Well, I want to pick region number 1. I'm trying to test the behavior of the vector field along the line m is equal to 0 in this region that I'm calling region number 1, between D is equal to 0 and D is equal to 3. So what is an appropriate point for me to choose? There's more than one right answer to this question. So I want to see what people are thinking. Go ahead and suggest a point for me to test. Remember that you need to suggest a point in D, M format. Okay, so use D, M format is equal to, and I'm going to wait for your suggestion, and then I'm going to use your suggestion. D, M. M is always equal to 0, right? And then D is going to be some number between 0 and 3. So someone's saying, how about 1, 0? That's perfect. Or 1.5, 0. Yeah, those both work. 5, 0. Or we could do a bunch of other things. There's so many test points we could pick. Or 2, 0, right? And then 4, 0 would be for region 2. Great. Okay, so you all are really understanding this. This is really great to work through. Right, and notice that for all the suggestions, so someone else suggested 2, 0. All of these are great suggestions for region 1. They have 2 things in common. The first thing that all these suggestions have in common is that the value for m is always 0. And it better be, because I'm working on the m is equal to 0 nullcline. So that's how everybody knew to put 0 in for m. That's the line that I'm working on. And then the other thing they have in common is that the first component is a number between 0 and 3. You don't want to pick 3, 0. What would happen if you picked 3, 0? You notice how I said strictly less than 3? I didn't say equals to 3. I want to see if you know. That's just an open question for you. If I accidentally thought 3, 0 was a good choice, that's an equilibrium point. Right. So if you chose the point 3, 0, then you would be hitting an actual equilibrium. So then you'd get d prime is equal to 0, and that's not going to be left, nor is it going to be right. So you don't want to pick the equilibrium point. Excellent job. Okay, so I'll just pick from any of these, knowing that you could just pick any of them. I'll pick 1, 0 as my test point, okay? And now I'm going to test d prime. And I'm going to see what the value of d prime is when I plug in the value 1 for d and 0 for m. Okay, so d prime is equal to d times 3 minus, all right, well, I know m's 0, but I'll just type it out anyway. 3 minus 2m minus d. And so plugging in a 1 for d and 0 for m, I get 1 for d, 0 for m, 0 minus 1, that's a 2 inside there, times 1, and that's 2. Okay, so I got that d prime is equal to 2 at the test point. Here's my test point right here. I'm going to test at 1, 0. I'm testing what does the vector field look like here. And because we got the value of 2 for d prime, can you please tell me, should I draw a left pointing arrow or a right pointing arrow? What should I draw for my vector field? When I do draw that arrow, I'm going to use my blue pen to draw it because it is a component of the d variable. I'm just checking in with what Alan did here. He actually drew the vectors in green, but I've been trying to use the same color as the variable I'm trying to describe. And everyone's saying point it to the right, and you're totally right, because this is a value. Oh, I know that's pointing to the right. Maybe I should stop drawing arrows for there, but yeah. See, the vector field's pointing to the right. Now, if you happen to pick a test point like 1.5, 0, you would still get a positive value. If you pick 2, 0, you would still get a positive value. No matter what you picked inside this region, you would always get a positive value. They're not all going to be equal to 2, but they are all going to be greater than 0. So that's what we say they're qualitatively the same. They're not quantitatively the same. So you evaluate the vector field at 2, you're not going to get 2, 0. You might get 1, 0. But they're all positive. And so in that way, they have the same quality that they're all pointing to the right. And guess what's going to happen when we choose a different test point for region number 2? I'll use a suggestion that somebody had already mentioned, which was to use, for testing region number 2, I'll use the point 4, 0, because that's on the other side of the equilibrium point. So now I'm going to test region number 2. Okay, and over here in region number 2, that's the places where d is greater than 3. Okay, so d greater than 3. And somebody had already suggested in the chat box earlier, an appropriate test point is 4, 0. And then just plugging that into the d prime equation, just to repeat it here so you can see exactly where I'm plugging it in. 3 minus 2m minus d, that's going to be 4 times 3 minus 2 times 0 minus 4. Okay, so if I use the test point 4 comma 0, which is all the way over here, now I'm going to test number 2. I'm going to use 4 comma 0. It's on the other side of the equilibrium point here. And I got a value that's 4 times 3 minus 4, which is minus 1. So minus 4. Okay, minus 4 is a negative number, and that means it's pointing to the left. And so over here in this region right here, and this is going to be true about any test point that I choose in the region where d is greater than 3 and m is equal to 0, is that's going to be pointing to the left, to the left, to the left. This one is to the right, that one is to the left, and right here is going to be 0, right? So you can see that their forces are pointing towards 3 comma 0, and that tells me that there's at least one dimension of stability in this fixed point here, is because I can see that things are going towards it. It's an attractor, at least along the M nullcline. Sweet. I hope that everybody understood all that. And now I would like to explain the method that I use in my videos, because it's just more of a visual. Instead of using this test point stuff, I kind of like to use a graphical reasoning to derive these same arrows. So I'll try to explain that out, and let me know if it catches your fancy, or if you have some questions about it, okay? So this is just an alternative, a different way to reason out the conclusion that I just found. And I'm still going to work on the m is equal to 0 nullcline. Okay, and I'm going to show you a graphical method. So this is a graphical reasoning instead of test points. Okay, now for the graphical reasoning, I'm going to start just by throwing in the assumption that m is equal to 0. Just a second. Can you reiterate how you draw the to reiterate what I just did? I'm going to reiterate what I just did again with this other method, but in case that the question that you just entered is speaking to what I just did over there, remember that when I use this test point number 2, I've already erased the board over there, but the work I had on the board was that when I plugged in the point 4 comma 0 into the d prime equation, I got d prime is equal to negative 4. Okay? And if you recall the algebra that I went through to get this here, the conclusion that d prime is equal to negative 4 is how I drew the conclusion that the blue rate of change for d. If it's negative, it means that d is getting to be less. It's getting reduced. And so things are moving in the left direction. Okay, so the negative 4 is directly tied to pointing it to the left. If that didn't answer your question, please type in some more, because I definitely want to make that as clear as possible. So I'm going to go on to the graphical reasoning method now, and I'm wondering if I answered your question. If there's still confusion, please let me know. Okay, so for this method, I'm just going to do my same d prime that I did before. And this is a method that I use in my videos that I recorded for this week because I think it's just a little more fun. I'm going to plug in the assumption that m is equal to 0, because you can see that's the assumption I have right there. And so plugging in the assumption that m is equal to 0 leads me to the statement that d prime is equal to d times 3 minus d. Okay? So for this part, I plugged in m is equal to 0 here, and that's what eliminated that term. Okay? Now for this analysis, all I want to do is I just recognize that this is a familiar form to me. I could graph this from pre-calculus when I learned about quadratic formula, when I learned about quadratic equations and parabolas. This is a down-facing parabola with roots at 0 and 3. So the reasoning that I'm using is making use of my pre-calculus knowledge. This is a down-facing parabola with its roots at 0 and 3. Okay, so what I'm saying is, if I looked at a graph, of d prime, it's going to look like this. It's a function of d, here's d prime, and it's a down-facing parabola with its roots at 0 and 3. Okay? That's what I drew on the board in my other videos. Now, how did I use this little image of a frowny face to determine whether I'm going to have right or left pointing arrows? Well, I have to know how to read this graph. So that's one thing that the graphical method relies on, is your understanding of what you're interpreting from this graph. Let me write it over there too, so I can really clearly lay out this other method. Okay. This is an alternative to doing the test point method. So I'm going to erase the test points because I actually don't need them. So the alternative method is on the nullcline m is equal to 0. We're going to look at d prime. Okay? We're going to think about it graphically. D prime as a function of d is positive in the region where d is between 0 and 3, and it's negative in the regions outside of that. Okay? So I'm just going to explain it. Let me know if you understand what I'm explaining, or if you don't, please let me know your questions. It's not going to be useful to you unless you really know what I'm talking about here. I'm looking at this picture, which is a description of the actual d prime equation on the m nullcline. And this picture tells me that d prime is greater than 0 between 0 and 3. And that d prime is less than 0 when d is greater than 0. When d is greater than 3. I'm sorry. Okay? So my conclusions that I'm drawing are that d prime is greater than 0 on the interval z is between d and 3. And over here, my conclusion is that d prime is less than 0 on the interval where d is greater than 3. Okay? And then the interpretation from that graphical analysis is what leads me to know what arrows to draw right here. Right? Because, and I'm saying that the rate of change of d, which is the horizontal component of the vector field, is a positive number. Positive numbers mean point to the right. On the interval between 0 and 3, it's always pointing to the right. It actually gives me a little more information than test points, because it tells me the magnitude of the vector that I can just read right off the graph. So let me show you how much information I'm really getting from this graphical method. You see I'm erasing all those arrows I drew? Because it's telling me that these arrows are going to be pointing to the right, and they're going to have small magnitude, bigger, bigger, bigger. They're going to have their biggest magnitude right at the vertex, which is located at the average of the two roots. So right here at 1.5, is where I'm going to have my biggest right vector. Okay? Over here near 0, I'm going to have a vector that's pointing to the right, but it's going to have a smaller magnitude. So I'm going to have like little vectors that get bigger, and they get bigger, and they get bigger. And then they're biggest right here, where the parabola is at its peak. And then they get smaller and smaller and smaller, always pointing to the right. See, and then as I approach the number 3, those right pointing vectors are getting smaller and smaller and smaller. It's kind of like I'm visualizing myself doing test points for pretty much every single value between 0 and 3. Remember before where I was like, okay, pick a value. Some people picked 1, some people picked 2. One person picked 1.5. And I can see the output from having plugged that into my equation right here. This graph is telling me the output for every possible test point that I could have picked. And so I get all the information, not only of the direction, but also of the magnitude of these purely horizontal vectors in the vector fields along that nullcline. It's really nice. Likewise, over here, when the parabola is dipping below the horizontal axis, it's telling me that there's going to be left-pointing behavior on the interval where d is greater than 3, and that close to the number 3, it's going to be a small magnitude vector. And then as I get bigger and bigger and bigger in d, the vector field is pointing harder and harder to the left over like that. Okay, so it gives me a lot more information. Did you all understand that, though? Do you like that method? Do you get it? Or should we just stick with the method of test points? That's what I want to know. Hopefully some of you are still watching. I know it's been kind of a long session. I'm going to wrap this session up just by doing this for the other nullcline as well. But I wonder, do you like the method of test points better? Or do you like that graphical method that I just introduced better? If you get, or in which way you'd like to see me do the other one. The graphical method makes a lot of somebody. That's great. That's great. Me too. I like the graphical method too. Because it's basically giving me all the test points info all at once. Some people like the algebra of test points though. And really, everybody's got a different way that they think. Some people might understand the algebra better. Some people might just see the graph pop into their head like I do. Yeah, more information is really obtained by looking at the graph. Hopefully you know what I mean by being able to see what the test point values output would be, no matter which test point I pick in this region, by viewing the graph. So that's why I prefer the graphical method. It's giving me more information, but I can certainly illustrate both methods again on this second nullcline. So now I'm going to do the nullcline m is equal to 2 minus d. Yeah, you can use Desmos. Great idea. Yeah. So if you don't see pictures of parabolas floating in your head all day, maybe like your math professor, then go ahead and use Desmos, definitely, because it'll allow you to see that picture and guarantee that you're on the right track. Yeah. The thing about Desmos is it's just a tool, and it's of no use to us if we don't know what we're doing with it. And so you can certainly use Desmos to do this, but you have to know what I graphed. Did you see how I derived the equation of what to graph? Let's go through that again for the other nullcline, because on the other nullcline it's a little more complicated. And that way we'll know how to use the tool of Desmos or any other graphing tool that you want to use. Okay, so this will be the last part of our YouTube Live today, is that we're going to repeat what we just did, but for the m is equal to 2 minus d nullcline. Okay, I'm going to need a little more space on this board. And because I know that the m prime equation is not going to be used because I'm on an m nullcline, I'm just going to erase the m prime equation. So I get a little more space here to work out the algebra of this. And we'll show the method of test points, and we'll show the graphical analysis. And we'll get some arrows drawn. Okay, so now we're going to refocus our attention to the other nullcline, m is equal to 2 minus d. Now we're going to try to draw either purely left or purely right pointing arrows, depending on the sign that we get when we analyze d prime on the m nullcline. Okay, so now we're going to work on the other m nullcline. This is going to be on m is equal to 2 minus d. Okay, and once again, we need to plug into the d prime equation so that we can make a conclusion about whether it's pointing to the left or to the right. Okay, so here we go. D prime is equal to d times 3 minus 2m. Now, where I see the m right here, I'm going to plug in the nullcline. That's the same thing that I did last time. Just checking. Okay, good. So you see where the m is here? I'm going to cut right to the chase, and I'm going to replace the m that's supposed to be right here with the statement of the nullcline, which is that m is equal to 2 minus d. I'm going to plug that right in. So I kind of skipped a step. This is the m that's in the equation right there, and I replaced it with the statement of the line that I'm analyzing the vector field on, which is the second m nullcline. Now I'm going to try to simplify this algebraically, particularly the inside part. So minus 4, multiplying this out, minus 2 times 2 is minus 4, minus 2 times minus d is plus 2d, and then minus d. And so then I can simplify it even more to get d times d, 1d minus 1. D minus 1. Okay, I'll start with my fave, which is the graphical method, and then we'll talk about the test points confirming the conclusions that we get from that. Just like last time, I have a statement about d prime and how it's related to d. And now on the side here, or use Desmos if you don't want to graph this by hand, I'm going to just image. I'm going to take a look at what this is telling me. Okay, so I'm going to draw a graph of d and then versus d prime over here. And you can see that the two roots are, one root is 0 and the other root is 1. And this one's actually an up-facing parabola. Does everybody know how I know whether this is an up or a down-facing parabola? Do you remember? It has to do with the coefficient on the squared term. Okay, so I'll just put a little reminder in case that helps you out. Because you're like, how the heck did I know that? Well, factoring this out to d squared minus d, I can see that the coefficient on the squared term is a positive coefficient, and that corresponds to an up-facing parabola. On the last example, the coefficient on the d squared was a minus 1. That's why I knew it was a down-facing parabola. Okay, so this is an up-facing parabola with roots at 0 and 1, so it looks like this. Okay, and that's the same thing that you would get if you graphed this equation on Desmos. Let me just write this on the side if you want to play along on Desmos. The thing about Desmos is, go to desmos.com for free beautiful graphing, is that you should type the independent variable in as little x because that's what it expects. And the dependent variable here is usually y. So instead of typing, you don't want to type d prime equals d squared minus d. You would want to type y is equal to x squared minus x. That's what you would type if you were going to use Desmos. It's a good thought to practice using that. And hopefully you understand that this is how I would type it in, even though that is really what I'm working for in terms of my equations. So that's what I mean about having to understand how to use a tool to make it useful, is that you really have to, digest this in your brain, that here I'm just trying to visualize the behavior of the rate of change of d as it depends on d. Okay, so if you do type it in that way, let me just copy it over here to remind us of our conclusions we'll draw. Here's 1, here's d prime. Okay, so the conclusion that we're going to draw from this is that between 0 and 1, d prime is negative. And from 1 onward towards infinity, d prime is positive. Okay, so I'm going to write that conclusion on the board, and then I encourage you all to map that onto what it means about the nullcline. Okay, so what I'm saying here is on the interval between 0 and 1, d prime is negative. Okay, and then on the interval where d is greater than 1, d prime is positive. Do you know what that means for the arrows? Okay, great. So let's draw it on there, right? And this is really confirming that we're on the right track, because when I went through this analysis and I saw there's a root at 1, 1's a dividing line between negative and positive behavior, that exactly matches up from my previous work in question number 5, where I located a fixed point, or an equilibrium point, right at the point 1. You see, so that's not a coincidence. That happens every time. Is that the sign of your non-zero equation is going to flip sign after you pass through an equilibrium point. Okay, so that's good. That's a good sign that I'm on the right track. The fact that I found this dividing line at d is equal to 1, and I see an equilibrium point where d is different. The statements that I've written here in terms of what I should draw with my blue pen. Okay, so between 0 and 1, D prime is negative, so that means I'm going to draw things that are pointing to the left. Okay. In fact, if you want to be a stickler, what this tells you is that the biggest, the most negative vector is going to occur right here where D is equal to a half. Okay, so I actually drew it a little wrong because the other arrows are going to be smaller. So let me draw all the information that I'm possibly seeing by using this graphical method. Is that right here where the vertex is, that's where the magnitude of the vector is going to be at its peak, right? And so it's pointing to the left as much as it's going to right here at 0.5. And then as we get closer to the fixed point, it's pointing to the left, but smaller amounts. And here it's smaller, and then as we approach the point of 2, it's still pointing to the left, but in smaller and smaller amounts. And that's because the parabola is approaching 0 as we get closer to that fixed point. Okay, likewise over here in the region where D is greater than 1, the parabola is getting bigger and bigger and bigger ad infinitum. And so what that's telling me is it's going to point a little bit to the right, and as I veer away from that fixed point, it's going to point more and more and more to the right. Okay? And all along this line, even as it goes into the fourth quadrant, it would still be pointing more and more to the right. I'm just not focused on the fourth quadrant because the only quadrant that is of interest in ecological context is going to be positive M and positive D. So that's why I'm just focused on the first quadrant, although truly mathematically speaking, you could analyze the whole plane. Okay, so the last thing I'm going to do is just do this again with the test points. This will be your last chance to ask any questions or put in any further requests after I do the test points. If I don't see any more questions or requests, I'll close it out for today. Okay, so let's just do the test points so that we can confirm what we already know from the graphical method. And as we already explained, we're going to need to test in 2 different regions. There's going to be a test point for this region in between these 2 fixed points. Then there's going to be another test point in this region, which is beyond that fixed point. So when I use the test points, I have 2 regions. Okay, and region, what I'm going to call region number 1, that's right here, where D is between 0 and 1. See, I'm just making a statement about D. So D is between 0 and 1. And I can pick any point between 0 and 1 for the D. I don't know if anybody's left with any energy in them, but if there's anyone out there who wants to suggest a test point, I'd like to see how much math you can really do in a day. Are you still there? Are you still working on this one? 0.5, right. But it's even harder than that because 0.5 is the value for D, but what's the value for M? Right? So somebody else has said 0.5 comma 0, but if it was 0.5 comma 0, it would be down here on the other nullcline. That's not the nullcline we're working on anymore. We're trying to work on this nullcline. So what's the value of M? Oh, wait, right? Whoops, it's okay. Mistakes are where learning happens, right? So this is a very common mistake is once you pick an appropriate value for D, you have to figure out what the value for M is going to be. You have 1.5 for D. I think 0.5 is a very good choice to pick for D. So maybe we can do a test point at D is equal to 0.5. You see how D is equal to 0.5 satisfies the interval that I'm working on for this region? So the question is, what's M? What's M equal to? Because I need to know, like, my test point is right here. It's along the line M is equal to D, but let me just emphasize where it is. M is equal to 2 minus D, I mean, but if you're going to pick this point right here to test point, D is equal to 0.5, how are you supposed to figure out what M is? Somebody says 0.5, 1.5. That's right. You know how you find out what m is? Well, this whole time, it says it right here. That's the nullcline that you're working on. Once you pick a value for d, you plug it into the nullcline equation to get the component, the other component. Okay, so what's m? Well, we're on the line, m is equal to 2 minus d. That's the nullcline that we're working on, right? It says it right here. So if I pick the point 0.5 for d, then my m is going to be 2 minus that. Okay? So m is equal to 2 minus the point that I picked, 0.5. So m is equal to 1.5. So that's my test point, 0.5, comma 1.5. Tricky. I didn't have to do this when I was doing the graphical method. Remember? I didn't have to do that. So that's another reason why I like this. Is once you understand this, you actually have to do less number crunching because the picture's crunching the numbers for you. So that's another reason why I like that. But it's a good lesson to really solidify our understanding of exactly what we're doing. Okay, so now that we know our test point, hopefully everybody understands the explanation of how we equation and then draw a conclusion based on whether I get positive or negative amount out. Okay, so I'll just do that over here. All right, and so we have test point 0.5, comma 1.5 for region number 1. And then we're going to plug it into the d prime equation. So d prime is equal to d 0.5, 3 minus 2m, 1.5, minus d 0.5. And now we have to crunch all that stuff out. 0.5 times 3 minus 3, oh, that's convenient, minus 0.5, and so I get negative 0 thing. But is it good to confirm it, right? The region this is pointing to the left is because the actual vector field, evaluated at the point 0.5, 1.5 is negative 0.25, comma 0. Okay, that's a good confirmation of the understanding. I'm going to write that down. So the vector field itself, the vector field at the point 0.5, comma 1.5 is negative 0.25 for the d prime, comma 0 for the m prime. This is the value that I just got from the d prime equation, and I know the m prime would equal 0 because it's on m nullcline. That's what defined it. So this is d prime, comma m prime. Okay. So this little blue vector that I drew right here is literally the vector negative 0.25, comma 0. All right, final thing. What test point should I use for the second region? You see I have this other region all the way over here. Along the line, m equals 2 minus d with d greater than 1. Can somebody please provide me with a test point, and then we'll finish with that. Okay, like I was just saying, we're going to move on to region number 2. And that's the region where d is strictly greater than 1. And we have to choose a test point for that region. I'm going to erase this other test point because we already went through that. Okay, so now we're trying to do region number 2, which is over here. It's on the m nullcline, where, again, the statement is m is equal to 2 minus d. But now we're in this part of the region here, where d is greater than 1. And somebody says 1.5, comma 0.5. Perfect. That's great. Any value of d that's greater than 1 is going to be an appropriate value. So we can choose d is equal to 1.5. And then remember that in order to figure out, here's test point number 2, 1.5, comma, To figure out what m is, we have to plug it in to the m nullcline, okay? And so m is equal to 2 minus d, which is 2 minus 1.5, which is 0.5. So that's where I got the second component of my test point. That's my test point. I can actually keep most of my writing on the board. Okay, so this is for region number 2. I'm choosing the test point 1.5, 0.5. In the d prime equation, I'm going to replace d with 1.5. I'm going to replace m with 0.5. I'm going to replace d with 1.5. Ah, geez. You're going to make me think on camera? Does anybody know what this value is? Let's see if I can figure it out, but maybe you can figure it out faster with your calculator. Does anybody want to crunch out what d prime is for me here as I try to mull it over? 0.5, so this is going to be 1.5 times 0.5, which is 0.75. Yes, 0.75, perfect. We're both on the same page. Great. So you see, d prime is equal to 0.75, and that's a positive amount. And so just like I had already drawn with my blue arrows before, I know that at this test point, the vector field at this test point is literally equal to 0.75 for the d prime, comma 0 for the m prime. That's why it's just horizontally pointing to the right, and it doesn't have any up or down components. Okay, so that was a lot of work for Tuesday. I hope you had some fun doing that, and I hope you feel like you're really going to have a good head start on the homework, which I feel like you do. Thanks for watching, everybody, and I'll see you again on Thursday. Don't forget to bring your homework questions, what's left of them, by Thursday, so we can get right to the point and make that a really good working session. You're welcome. Thanks for your support, and I'm really glad to be here for you. Thanks for interacting through the polls with me. I'll see you on Thursday.